Okay, let's try the apparent weight in an elevator problem, which is 26. You want to draw your free body diagram on that thing. So let's take a look at doing that. We've got the person standing on a scale here inside an elevator. So the forces on that person would be the force of gravity pulling that person down, and the normal force pushing that person up. And your scale actually reads the normal force. It doesn't read the actual weight. So that's why we call it apparent weight, what your weight appears like when you're on that, standing on it in the elevator. So we look at A. A says, what does the scale read when the elevator accelerates upward at 3 meters per second squared? When you do that and you're standing in an elevator, it feels like you're heavier than what you really are. So we should see a reading on that scale that's going to be greater than 1,000 newtons. It's going to make the apparent weight of the person larger. So how will that work? So let's do our equation. Sum of all the forces is equal to the mass times the acceleration due to on the object. So you've got two forces, okay, and if it's accelerating upwards, let's make the normal force positive and the force of gravity negative. So we have this here. Now we need to solve for the normal force to see what the scale reads, because again the scale reading is the normal force. So we'll solve for that. Take MA plus MG here. And then we can start plugging into some numbers. Well, what is the mass of that person? We come up here. We know the weight is 1,000 newtons. Remember, weight is equal to mg. To solve for mass, and we'll just get rid of g over here and move it over here. So the weight divided by the acceleration due to gravity will give us the mass. So mass would be 1,000 divided by 10. 9.8, but we're using 10. So the mass would be 100 kilograms. So we want to make sure to plug in 100 kilograms here. Says the acceleration of the system would be 3 meters per second squared there, so we'll put 3 there, plus the weight of the person, which would be 1,000 newtons, or 100 times 10. And so the scale here would read 300 plus 1,000, or 1,300 newtons. So that scale would read 1,300 newtons. Slightly larger than the original weight. The person were only standing on the scale, not accelerating in an elevator. Now, what does the scale read when the elevator accelerates downward at 3 meters per second squared? Now it's going to be going downward, so we've got to change the direction of acceleration. So I'm going to come up here and change that. Okay, so now it's going to accelerate downwards. Up is no longer positive, it's now negative, and down is not negative, it's now positive. Why? Because the direction of acceleration is down now. So let's come back to second law. Sum of the forces is equal to MA. Right now we've got positive mg and negative Fn are equal to MA. Okay. Well, again, what do we need to be solving for? Which one of these forces is the scale reading? The normal force is the scale reading. So we've got to read that normal force up here. And therefore we've got to solve for normal force down here. Right, so we could say negative Fn is equal to ma minus mg. So that's negative Fn. So then we need to flip the signs. And when you flip those signs, it would be negative ma plus mg, or really we would probably write it mg minus ma here. It's really probably how you write that formula out. So then you just plug in your numbers to solve for normal force. Mass being 100, acceleration due to gravity being 10, mass being 100, and now our acceleration is going to be 3 meters per second squared. Okay, so our normal force would be 1,000 minus 300, and that gives us 700 newtons. Okay. Part C says, if the scale reads 1,500 newtons, what is the elevator's acceleration? So we can go through and create a formula for this. How would we do that? What do we need to go through to do that? So as we look at this, you know that this 1,500 is greater than 1,000, so then we can say the direction of acceleration is going to be upwards. So that means up is positive, down's negative there. Okay. We still are going to have the same diagram. So we would just say Fn minus mg is equal to ma. Okay, I'm just doing the sum of the forces is equal to ma here. All right, and then we would just solve for a this time. So I would need to divide out mass here and divide out mass here. So now I can plug in some numbers. I know the normal force is 1,500 minus the weight of the object, which would be 1,000, or we can say the mass, which is 100 times 10, is 1,000, divided by the mass, which is 100, is equal to the acceleration. So 1,500 minus 1,000 divided by 100. Okay. So that would be 500 divided by 100, which is 5 meters per second squared, and that is our acceleration of that object.